So welcome back. Good morning and welcome back. Yeah, today is the third and the last lecture of Bernard on fluctuations for non-equilibrium systems. Please.
Okay. First, I want to say that I'm very happy to be here, and I want to thank the organizers again for this very nice stay in Cambridge. And the other also thing I want to say is that you see here, I present it as an introduction, and the thing I chose to discuss are things I understand best myself. And it does not mean that I cover the whole subject, and in particular, there are a number of important contributions, including work by people who are here, and which I do not cover, but maybe it will help if you are interested these lectures will help you to enter the subject more and to look at their work. Okay, so today I want to talk about current fluctuations of the current and large deviations of the current. Again, I am discussing a diffusive system. So you remember I have drawn this picture many times. I have a large system, and then the two basic quantities that we had was d of O and sigma of O, and they were defined as if ρ1 equals ρ2, then the fluctuation is sigma of O over N, and if ρ1 minus ρ2 is small, then Q is d of O times ρ1 minus ρ2 over N. So this is called Fick's law, and the two things are related by fluctuation and dissipation. Now, the question, okay, you can have many questions. And for example, you could say, what happens if ρ1 minus ρ2 is not small? Okay, can I calculate the same quantities when it's not small? So it's interesting. Question to ask, whether you can tell what are the higher cumulants of Q. So this means you want a root distribution of Q, in particular, whether you can discuss or study over geometries. Like, for example, if you, instead of having your system like this, you take a system which is on a ring. Okay, so in principle, the system will reach equilibrium, but still you can look at what are the fluctuations of the current, because you see you have a diffusive system, some particle will cross here, and you can ask what happens. Towards the end, I will mention briefly what happens on an infinite line. Even at equilibrium, you can say, okay, I have an infinite line with a certain density rho, and now I sit here, for example, that's a question, and I ask how many particles have crossed this point, or you could ask more complicated things, and what is the distribution of this Q? You could also, and okay, a number of these things have been done. There are some partial results on it. You could say that you have several species of particles. In which case, for example, the current of the species alpha would be a matrix D alpha beta of rho beta 1 minus rho of beta 2, and there is some over beta, so D would become a matrix, and also the Q, you will have correlations between the current of the two species, so sigma also will be a matrix, they will still be related. In fact, they are related, but what is called the Onsager relation, okay? You can ask what happens if you are in higher dimension? So, for example, instead of having this geometry, I have here the system. Here I put a contact with a reservoir at density ρ1 and over ρ2, and then there will be a flow of particles. There could be non-conserved field with some reactions, and like I think some models of active matter belong to this class, or also to this other class. Okay, so you have a very long list of things you can try to do. Okay, so here it's two dimension. Okay, it would be L here also to be different. Sorry? In 2 dimensions? So, sorry, here there would be a L. Yes, sorry. And this would depend on all the densities. Yes, sorry. Yeah. Sorry, there is a parenthesis there. Okay. So you can imagine a lot of things. Okay, so I will essentially concentrate on that, and I will say a few things about the ring geometry and this infinite, but there are maybe there are lots, as I said before, there are lots of works which have been done, and here I just mentioned things I think I know, okay, and principles that I should know because I was an author of the paper. So let me come to here, and to quantity, okay, one quantity you might like to study, if you are interested in current fluctuations, is the large deviation function of the current, now, not the density. And so what I want to discuss first is the convexity of the large deviation function. So now, we are not discussing the density, but you look at the system now during a long time, and you see that the probability, you ask what is the probability that the total current you have, or the integrated current, that is the total number of particles which have crossed certain section, going that way minus the number going the other way, so the integrated current is G. I try to be consistent with the notation of last time, so these are microscopic quantity. Really, that's the true current, that's the true quantity. And okay, in general, this will be minus 2, a certain function which will depend on this current J, ρ1, and ρ2. And this, you expect it to be true, even if the system is not large. There is this large deviation function. Even people, what they call quantum dots, would be a system where the system can be in 2 states. It could be occupied by a particle or empty, and then you would have a current from left to right, and then you could ask this question. But I think here, at some stage, I want to discuss the case of diffusive system. But okay, so one way is to say I want to find this large deviation function, which depends on this quantity, and of course on the system you look at. And this is something you expect for large time, because at short time it will depend on what you start with, whether the initial configuration is something or something else. But if you wait for very long in the steady state, then the system will forget its initial condition. And okay, now okay, often then you might be, instead of looking at this large deviation function, you might look at a generating function of this current. And of course, G of lambda is the maximum over J. There is this Lagrange transform. lambda J, lambda of J, sorry, yes, minus f of J. So, okay, so depending on what you prefer, you might prefer to compute the G or the F. Okay, but the important thing is that always, or f of J, okay, if you have a system which has a relaxation time, whether it's large or small, f of J is always a convex function of G. And that's very easy to understand. Imagine that I look at my system over a long time, and then I say, okay, during a certain, so I have a very long time too, and during the first part of this time, I have observed a current J1, and for the second part of this time, I have observed a current J2. So the total flux I am going to see will correspond to a Q over T, which is just J, which is J1x plus J2, 1 minus x. And if you want to think about all the possible events which will produce a current J in the system for very long, you have these events, but you have many others. So the probability of this, of seeing this is certainly less than the probability of seeing J for the whole system, because this is a particular case of having the total current. This is just one strategy, but you could say, I choose J1 prime and here J2 prime in order to satisfy also the same thing. Okay, so just because of that, it implies that the probability of this that you can write in terms of f of J1 and f of J2, because the times are very long, then it will there will be an inequality with f of J that I write, and this is called convexity. So this is a little bit reminiscent of the convexity of free energy. So this quantity has a lot of similarities with the free energy in equilibrium system. So if you do what I was saying, then you would say that the probability that Q over 2 is equal to J is larger or equal to the probability that Q1, that is J1 to X, okay, so the probability of J1, okay, so this is during time tau, and this is during time tau X of J1 times the probability of J2 during time no 1 moment. And from that, you get the convexity that f of x of J1 plus 1 minus x of J2 is less or equal to x f of J1 plus 1 minus x f to J. It's important to have that in mind, because you will see there are some solutions, and sometimes these solutions it turns out that they don't satisfy this property, and so it tells you that the solutions are wrong. Okay, so this is the convexity. Now let's come back to the large deviation of current for diffusive system. So what I told you here, that's not the only thing which is important is that time is large. It doesn't matter whether the system is small or large. And in fact, when I write this inequality, you want really to be careful. You have to put bounds on what happens just here near the boundary, but this is totally negligible. Okay, so now let me talk about the large deviation function of the current for diffusive system. Now, last time we discussed the large deviation function of the density. And in fact, it turns out that there is this rule theory, but somehow this, if you take a generic system with a sigma and a d, usually you cannot calculate. Now I want to tell you that for this large deviation function of the current, the probability that Q over 2 equals J, exponential minus 2 equals J, which now will depend on the system size. This we can compute for arbitrary sigma and arbitrary sigma of O, and D of O can be arbitrary. Under some conditions that I will discuss. Okay. So I want to explain that, but to do that, you see here I am really talking about the true current, true number of particles. Here I have the microscopic time, and this is a microscopic current. And so if you remember, there is this relation between the microscopic world and the macroscopic. Okay, so if you count the number of particles in both sides, in both sides, then they would be the same. Okay, I did not write that in my notes, so I think it's true. Hopefully, maybe I put it in parentheses because maybe I won't need it. Okay, then the microscopic time. Here there is a macroscopic time, and they're related by L squared T. Then there is the macroscopic distance, and here there is the microscopic. Here X is L times T, and the density is the same on both sides. Okay. Now, what is the probability? So this means
that's X equals L between X.
and X. Yes, but the important thing that I did not say is that the current here is equal. There is a macroscopic current of order 1, but there is a relation between the macroscopic and the microscopic current, which is given by this. So that's what we saw. And so this probability, in fact, from the macroscopic fluctuation theory, tells us the following, that it should be, okay, the system will evolve in time and the fluctuations, you see, after all this has to do with fluctuation, then it will be given by, to take the macroscopic fluctuation theory, by the maximum L times integral. So here is macroscopic time, macroscopic space, is with 0.45 square over 2 sigma. Now, here, J, rho depends on space and on time. So, because there is an L here, you would expect this to be the maximum over the optimal J of X and T prime and rho of X and T prime. And so you have to find the optimum of that. And now you have two constraints to that. First is conservation law. 0 over Tt prime is minus d over x, j over x and t prime. And the other constraint is that you would like that the integral over time, j of x and t prime, is equal to Lj. You want that the total flux is given by. So you want to find the optimum over all functions, that, and the maximum, so the exponential of the maximum. Okay, so you want to choose over all possible functions which satisfy that, the optimum. Okay, and so with theory, we here in 20 years ago, we felt that maybe we can do something, and we decided that Okay, first here you see, first thing you notice is here I did not put X, just because if you look at very long time, the flux is essentially the same everywhere, except very small effects, which will not scale with time. And here, okay, here I have tau, but I have four button, because, yes. And so the main thing that we did with Thierry was the following, was to say, okay, the optimum will be achieved by current which does not depend on time. So we say, okay, J of X and T. So if it does not depend on time, then it cannot depend on X, just because the flux is conserved in one dimension. So we say, in fact, J of X, the optimal one, will be just J constant. Okay. So this is an assumption. But when we wrote the paper, we did not think it was an assumption. We thought that this was right. And then if you do that, then you just find that FL of J there is equal to L times T times the minimum. So if J does not depend on time, then rho does not depend on time, but it depends on X. So it will be the minimum of rho of X of J, which now is just a constant, plus D rho times rho prime over 2 sigma of rho of X. So, and with the condition that rho of 0 is rho 1 and rho of 1 is rho 2. So we have to find the optimum of, sorry, and here there is an integral over X that I have forgotten. Okay, so the idea is that say, okay, I want to see events where the average current over a very long time is given. Okay, maybe these events are such that in fact the current is essentially constant all the time. Take this untypical value, but it's essentially constant. And so we have to find, if this is true, then we have to find the optimal sigma of the optimal rho of X. Okay. Now this is for physicists. Okay, when we wrote the paper, we did not make immediately the connection, but it turns out that this is a problem that physicists do all the time. You see, here, after all, it's a function of rho of X and a function of rho prime of X with some boundary values, and we want to find the optimum. And when you learn physics, you learn that you have L of Q and Q dot, Lagrangian, dt. So instead of being T, here it's X, but it's a function of Q and Q dot. And here it's a function of rho and rho dot. So we know how to solve it. And so what we did in that paper is to solve it. And I'm not going to write the equation, but we have the solution. And let me just, so this is just a mechanical system, because it's just a function of quantity rho of X and of the derivative. So let me tell you what are the results. Then coming out of it, then you can compute the average current and the second cumulant, third cumulant. In fact, we have a formula for all cumulants. So, okay, so this is the connected path over tau. Again, tau is the macroscopic time. And the result is that this is 1 over L times I1. Okay, I'll just say 1 over L I2 over I1. Okay, if I copied it correctly from the paper, I3 I1 minus I2 squared over I1 cube, and so on. And we have all the formula, but we have in fact the whole generating function, and the IN, they are just integral from rho 2 to rho 1 of G of O, sigma of O, n minus 1, G O. Okay, so somehow we have an expression for all the cumulants. And you see, it's true for arbitrary D and sigma. But, so we published this paper in 2004, and then 2005, our colleagues in Italy said, oh, that's not always true. And in fact, when they tried to prove it, okay, fortunately, they could prove it in some cases, but they said it's not always true. And they said, it's okay. So this is the group in Rome, Bertini, Desolé, Gabrielli, Jona-Lasinio, and Landim. Look, 2005. They say, yes, it's okay, but you need that sigma of O is concave. And if it's not concave, then this theory might not be correct, or at least the large deviation function that we could compute that way is not correct. And okay, so for the set, sigma of O equals 2 rho 1 minus 2, that's a concave function. For the random roots, 2 rho, that's concave, but it's certainly not convex. But there is another model. Maybe if somebody wants, I can ask a question and I can tell what it is, for which sigma of O is equal to 2 rho squared, and then it's convex, it's not concave, and so here there might be some problem. And so when we saw that, then we felt, okay, maybe something else happened. And in fact, what happens is that there is a phase transition that I want to discuss quickly. And so this means that here the maximum is not due to the situation where the J does not depend on time. Okay, and as I said, if it does not depend on time, it does not automatically, it cannot depend on X. But does not depend on time, it means the following thing is that you have your system, you have rho 1 here, rho 2 there. Okay, the average profile would be this. But in order to flow a current which is untypical, the system decides to choose a certain profile which will make more likely to flow a certain current. And there is an optimal profile to do that. So phase transition now will occur. Okay, so you could have phase transition even within this context by having that, say, when you vary this J, the optimal profile is this, and then at some critical value, still there is an optimal profile which does not depend on time, but which is different. So it could say that maybe for J less than J1, it's like this, and for a certain J critical, and for J larger than J critical, it would be there. Okay, the optimal profile. So it could jump also like that, but this would be still time independent and would be still part of this theory, because then you see you want to find the optimal path. But I think for people who have studied optics also, sometimes there are several paths which achieve the minimal action. So this is not a kind of phase transition I want to discuss. The only thing we could do then was to look for second order phase transition, because as physicists, we know first order transition for a nonlinear problem is very difficult. But second order phase transition, you can say that, okay, there is an optimal profile, which is time independent, rho of X and T prime in some rho tilde of X, time independent. and then you make a small perturbation, rho or delta rho, sorry, of x and t prime, and then the current will be J, which does not depend on x, because if the profile is constant, the current is M plus epsilon delta J of x and t prime. And then take this, you put it there, and you look at order epsilon square, and you see whether there is a mode which becomes unstable. And this is hard to do, because you are perturbing around the situation where the profile is not constant. The easiest would be that the profile is constant, then you would have some Fourier modes and so on. So the thing that we did, and to my knowledge, this kind of time-dependent fluctuations, when the profile is not constant, it's a difficult problem, like solving typical, like solving a Schrödinger equation when the potential is not constant. So, okay, usually you can maybe find approximate solutions, but you cannot. But situation where you can see this phase transition is if you do it on a ring geometry. So if you're on a ring geometry, there is no boundary problem anymore. Okay, it's very likely that if J is constant, okay, so if you take J is constant, it's rather convincing. Okay, now probably there is a simple proof, but I have not in my head now. But it would be to say that, okay, what the system does is that it has a constant current and a flat profile. And now you can ask whether when you change J, it's better to keep a constant profile, or maybe a profile which will start to be time dependent will be the best. And the situation is much easier because you are perturbing on a ring around the situation where rho tilde is constant. Okay, so you do this perturbation, and what you get is that, okay, there is an unstable mode which occurs when on the circle, on the ring, when the density, the average, okay, let's call rho zero, it's just a flat density, minus times sigma. Okay, so I copy what I showed in the paper, but I did not redo the calculation last night. It's negative. So if on a ring, the rho tilde of x is on rho zero, it's a flat, and you ask, okay, what is the best here? Is it on a ring to choose a flat density profile for a certain current J? And then it turns out that you find that it becomes unstable. So here I made a mistake. So it's sigma double. So it becomes unstable if this condition is satisfied.
So what's the factor in front of sigma double prime?
J
squared.
J squared, that's the current. Okay.
J squared.
So in fact, if on the ring, because the system would equilibrate, so the most likely current would be zero. But now you want a deviation from that. So at a certain, you can think of it as a certain critical value of the current, this becomes negative, and there is a phase transition. And you see here, you see very well that the fact that if sigma is convex, you might have this instability. If sigma is concave, then the second derivative is negative, and so you cannot get it. But of course, this is not a mathematical proof, but it's very consistent with what our colleagues in Rome said, that it's important, the convexity of sigma is important. So that's an easy calculation. What would be more difficult, and I would say I tried, but I did not succeed, is to start with a non-constant profile, like for the open system, and see when it becomes unstable. That was difficult. Something also which is difficult is to say maybe there is first order transition, so you cannot capture it by making a small perturbation like this. And then again, that's difficult. Now, somehow when you cross this phase transition, then the motion, okay, there is one unstable mode. So you expect the thing to become periodic. In the case that we studied with theory, we found that there is a profile which moves at a certain velocity or so on, but you cannot exclude that you have over bifurcations and so on, but the problem becomes non-linear. So okay, so that's one thing, and first order transition, as I said, is difficult. Okay. Please.
Question, but this is about large deviation.
Yeah.
So if you talk about the JC, this how I put it bigger than this. If you occur very unlikely.
Yes.
What do you think about the physical importance about?
Okay. So. Okay. Okay. This thing about large deviation. Okay, first keep that busy, so that's one. And you could say that's very rare event, and so who cares? Okay, so first, even if you are not looking at unlikely situations, in cases where you have several species of particles, then you can have phase transition, and the phase transition will be, okay, if they are second order, they will come out very much like this. So we say, okay, I have several species, I assume that there is a uniform density, the constant density, and then you will see that there might change parameters, and you see that there are transitions without talking about large deviation. But for typical situations, it's very similar. Now, you see, lots of people look at the tail of distribution. Okay, so this tells you that there will be some events which will be different from what you would obtain for smaller untypical values. But otherwise, I am not totally sure what maybe some people here have better ideas why these large deviations have any interest. But okay. So now I want to see, there has been a lot of work on this kind of system and so on. I am very brief. So I want to mention two other situations that I discussed briefly at the very beginning. Okay, so what if you look at higher dimension? I don't know what number it is on this slide. Higher dimension. Okay, so the thing we discussed is the one-dimensional case. And now I want to discuss higher dimension. So I go because of the blackboard, it's two-dimensional. I put into blackboard with that. But so here I have a contact with density ρ1, and here I have a contact with density ρ2. And now I want to ask the same question in higher dimension. Now, it turned out that, in fact, this was motivated by some works by some colleague. I have not written the name on my notes. So, okay, I prefer not to. Okay, from Holland, but okay. So in fact, they looked at this symmetric exclusion process, and they looked at it not in one dimension, but for some reason I am not totally sure of, they looked at them on fractals. And so they looked at the set with ρ1 equal 1 and ρ0 equal 0. So one side is empty, okay, no particle enters here, and particles enter there. And what they found on this fractal problem system is that they looked at the second cumulant divided by the first cumulant, and this is Okay, in electronics, people call it the Fano factor. And they find it 1/3 in one dimension and in two dimensions, not in two dimensions, say, so it's really Q squared divided by, in fact, sorry, I should be more precise. The connected part divided by Q was 1/3 on the fractal, very exactly the same as in one dimension. And then we reproduced it on the square lattice with a contact here. So in some work also, Thierry was involved and people from the Technion, also Ackermann and Spielberg. And so we saw numerically that the second cumulant was also 1/3. And we made a theory, and I'm just going to just tell you the result, is that that's not only true when this is for these densities, but it is true for arbitrary rho A and rho B, and for all cumulants. So somehow, the distribution of the current, if you are in one dimension and in higher dimension, is exactly the same. Okay. There are some small aspects that I think I have no time to discuss. If anybody is interested, I can discuss it more. I can explain what is the solution that how the solution was built and why there were some small discrepancies. Okay, maybe I would say the whole thing. Okay, so the story was the following: is first we want to write the equivalent of this action here for higher dimension. So the current will be a vector because and there is a V of rho, then will be now the gradient of rho squared over 2 sigma. Okay, so now rho is a function of space and J is a function of space in principle of time. And what we tried to find under the same assumption as in the previous work, we tried to find a J which is independent of time. And therefore, rho is also independent of time. So we tried to find what is the optimal current profile. If we assume that it's independent of time, it will flow a certain current from the left to the right, so from this, reservoir to this one, although it's 2 dimensions, but not only in 2 dimensions, in any dimension. Okay. And the answer is,
when you have dimensions, I guess D can be a matrix.
yes, but we took an isotrope.
Exactly.
I don't complicate. Okay, so in fact, the answer turns out to be the following. That okay, I think I wrote, okay. So I write it in. Okay, the answer is the following. If you have the solution of the 1D, so imagine that you have solved the problem with the 1D, and I would say rho optimal of X is the solution of the 1D problem. Now the answer is that what is it in higher dimension? Then you take the 2-dimensional system and first you solve the Laplace equation. So you solve Laplace V in this 0 with V at the boundary of the first reservoir, let me call it A and B, is rho 1, and V at the boundary of the second reservoir is rho 2. So here I just solve the Laplace equation with this boundary condition. And I have a certain V. And now the profile, the system, the optimal profile which the system will choose will be just rho optimal in dimension D will be the optimal profile in dimension 1 times V of R. So that now I have a kind of potential solution of this Laplace equation in dimension R. Okay, so it turns out that you write the optimal equation and so on, and then you put it in, you put it into you realize that this solves the equation that you want to solve. Although they are nonlinear, but the nonlinearity somehow that you have been able to solve for the 1D problem, they just are okay, turns out that they still solve in higher dimension. Okay, so now this is the paper we wrote, and we, of course, you see, I very much like, also first I enjoy to write programs, and the second thing is that even when I have a theory, then I very much like to see whether the program stays the same. And it turns out that, in fact, when we look at the two-dimensional case like that, so in fact the program was like this, and we compute the Q over Q, when the system is large, we found it is 1/3. But then we tried in 3 dimensions. And even the system becomes large, there was a small discrepancy. And I have never been able to resolve this discrepancy. So this means this does not look right, except that we made, with the program, it was easier to do something else, that is instead of having a contact in a single site, we made contact with a few more sites here. So somehow we did not put the contact at a single point, but we increased a little bit the range where there is a contact, and the situation improved. And so my belief is that in higher dimensions, the only thing you need is really that the contacts are big enough. And you see, when I work in the continuum here, I write the Laplacian in the continuum, but when I am on the lattice, okay, I need the range. I need first a very large lattice to start to resemble the continuum, but also this contact, I need also the contact to be large enough. Otherwise, you see, if you just look at the potential created by a single charge on a lattice, and okay, you have some small effect due to the lattice effect, and you have to spread the charge over a slightly larger region to find that the potential is Q over R. Otherwise, there is a kind of renormalized charge or something like that. So anyway, this was this is the link that we could do. Now, just the very last part that I want to mention. So please.
This is particularly for step, I think. Right?
No, I think I was not totally sure but when I read what we wrote in the paper, that's what I was. Okay, the simulations were done for the set, that's for sure. What is written in our paper is that it's done for sigma and D arbitrary. That's what we say. But last night I did not redo the computation. So hopefully we said it right, but often I find old papers and I don't understand what is inside, but many times it's just because I am decaying slightly slowly. So often I find that it's wrong what is in the paper. After a big effort, I agree with what I said in the past. But okay. What is written is that sigma and D can be arbitrary. Okay, so the last thing I want to discuss, which is more difficult, is the infinite line on infinite space, and even the simplest situation, which would be just imagine that you have a system with a certain constant density, so you start at somehow at equilibrium. system. So this is rho of x initially. And then you say for one question you can ask, many questions, but you say I am at the origin and I look at what is the flux of particles during time tau through the origin. And the system is diffusive. Okay. And the point is that first, because the system is diffusive, then the right thing to look at is Q of tau divided by square root tau. So instead of saying I want Q of tau divided by tau equals J, now you would say, okay, maybe I call it J. You can call it J if you like, but it's, you have something, the total current will scale like square root T, and the large deviation function will be like square root tau, sorry, because the microscopic time is tau, times a certain function V of C. So in principle, the quantity you want to look at is C. This okay, for example, is C, but usually things start to scale like square root T instead of T. Okay, so now just to give you a reason for that, again, I have to relate the microscopic world and the macroscopic world. So when we looked at this situation, we had a system of size L, we found that the probability of J was exponential minus L times T, the macroscopic times the function of J. Okay, now if you say that the true current is J over L, so this is microscopic, this is macroscopic. I tried to be so okay. So in the microscopic world, I have a certain current, I have a certain time, and Q is just J times tau typically, and this is J over L, so this is the macro quantity. Okay. The macro, this is L squared times T, which is and something like okay. So okay. But Q is exactly the same. Okay, you just count the number of particles, so the Q is exactly the same. And so if you just write this will be like exponential. So now you see, again, I am on a finite system, will be tau over L times a function of L times J. And J, this is exponential minus tau over L, because T is tau over L squared, times a function of L times Q over tau. Okay, so all this is valid for this one-dimensional system with that we have looked at all the time here. But now I say, okay, when I am in the infinite line, essentially the length which will matter, okay, of course, it's not the same situation, but the system is diffusive. So if I look at a time tau, essentially the only thing which matters is the region of order square root tau, because it's diffusive. So the length scales like the square root of time. So once I am here, I say the typical length which will matter are square root tau, and then you get this kind of relation. Here you will have exponential minus square root tau, and here also you will scale Q with square root tau. Okay, so this is just to give you an idea why you have this scaling. And now people have tried to compute, for example, this thing, and it's much more difficult. So see, in fact, with Antoine Gershenfeld, about 10 years ago, we did it by Bethe-Ansatz, but by lack of time, I will show you the Bethe-Ansatz solution now, because it will take too much time, and also because I did not we do it last night. Okay, but there are some extra difficulty here, which are the following: is that if you have a constant density and the system is infinite, okay, so you have a certain constant density, so you look, the system is at equilibrium. But in fact, the result that you are going to get here depends in a non-trivial way, I would say, on what you say about the initial condition. If you just see that the density is constant, that's not sufficient. You have to know something about the probability of the initial condition. So, for example, one thing that we called quench was to say that when you have this density, it's really this density. For example, quench density 1/2, so the step would be just every oversight is occupied. So this would be the initial configuration. That's at density 1/2. But anil would be that each site here is occupied with probability 1/2 and empty with probability 1/2. Okay, so these are two initial conditions, but okay, I think Mike wrote something about having over initial conditions, if I remember. No? Okay. Yes, okay. So you could say that, for example, the initial condition, I take the measure of an Ising model at a given temperature or whatever you want. It turns out that this thing here will depend on that. Okay, so what we have done, it turns out that the anil case is the simplest one, in quote marks, because although it's simple, it's not that simple. We could compute a few things with the better of that, but more recently, Tomohiro and some other people, they have been able to say more about even this case, but usually it's rather difficult. Let me just say one result, and I will finish with that. Which I found it surprising and which is rather easy to understand. So I started with a certain density. In fact, our paper was started even with two densities, rho minus and rho plus, near the origin. And we looked at what happens if Q is very large for the step, and we found that it decays this function here, okay, it behaves like Q cube over 4. Okay, so it's in fact really a function of square root 2 times square root 2 divided by oops. But it decays like exponential minus Q cube. It's not Gaussian at all for the set. And the question is there a simple way to understand it? And so, in fact, it will, and at least this was true for at least the quench. In fact, if I remember, we found even pi squared over 12, something like that. Yeah, I write this because there is a certain surprise that it does not depend on the density, the coefficient. And in fact, one way to understand it is to come back to a problem which is much simpler to solve, is to say, okay, I look at independent particles, and I am in the quench case, so whatever density you like. And then you ask, what is the probability that Q will be large? So, okay, so one thing is that you have to pay a certain price that these particles do not cross, but this does not cost too much. But you want lots of particles here to cross. Now, what's the probability that a particle which is at position X will cross? It's essentially, random walkers will be exponential X squared over 2, 2 or whatever. Okay, so that's the probability that this one will cross. Now it's quenched. This means that how many particles do I need to bring here? I need to bring a number of particles which is typically Q. So I need to do this product from x equal 1 to x equal 2. And if I do this product, I get exponential minus 2 cubed over complex. So, okay, so somehow, for this very simple problem, we find fluctuations which look a little strange, and one can understand it rather well, at least in this context. The pi squared over 12, I have no good reason to believe, but this kind of argument tells you also that it does not depend on rho minus and rho plus, provided that rho minus is not 0, because if it is 0, then, okay, you cannot bring particles on the other side, but that's it. Okay, so there are lots of things, as I said, which are known. I did not mention them because I tried to make things simple, and also I tried to talk about things I understand and not about things I don't understand. But many people have done important contributions. So I will stop there, but I want first to mention a number of people with whom I have been working on these things for many years. So I have worked maybe about 20 years ago, I worked with Jona-Lasinio and Jean Spear, and this large deviation function of the densities. And then I had a student a few years later, Camille, we continued these things. So when we put some asymmetry to the WhatsApp and a number of other things, there is also some common work with Joel. Then with Thierry, we worked on the large deviation of the current, and we made a number of papers together. And this thing about higher dimension was also done with Thierry and with Eric Ackermann. And Howard Spielberg about 10 years ago. This thing on this one-dimensional thing was done also with one of my students, Antoine Gershenfeld, about 10 years ago. And more recently, okay, I have been working with Pradeep Sadhu from Bombay, where we looked at, okay, we wrote two papers which are entitled large deviations on large deviations. So when we condition, so essentially we ask, you see, when we condition on the current, there is a certain profile, but now this profile itself fluctuates or even can have large deviations. So we try to compute things like that. So thanks a lot for both the invitation and for listening to all this.
Okay, thank you very much for the nice lectures. So are there any questions, comments?
Solve problems where you're not in just a position-like space, but in a phase space where there's velocities and positions, so densities and velocities. So large deviations with systems with inertia or gases where the motion is not diffusive. There.
Okay, so okay. I have maybe Thierry knows. Okay, what in fact the earlier work and some of the works which have been done, especially at the beginning with Joel Lebowitz, were things where we took what's called the accept. So where there is a velocity for particles, or there is a biased work other than the velocity. Okay, but in principle, I don't know. In principle, you can start with fluctuating hydrodynamics for the systems. I don't know how far you can go because I have not really worked on that. But I don't know. Maybe there are reasons you cannot. But I am not an expert.
Yuri, you have some comments? No?
Well, when we think about it, of course, it will depend very much on the model. For example, for one equation, we would have functional, again, position, velocity, which are different than which you can write. And after, you may wonder what to do with them. That's
I was wondering how far that enterprise can be taken for things like that.
But, okay. hasn't been done because the functional they are pretty heavy to study that very different structure than this one. But a priori, I mean, at least the setup and then minimizing and the type of question could certainly be asked whether they can be answered.
No, but you see, for the test sample, which is just very close to these models, then many of the things you do here do not work. Really.
Already for these.
Yes. So, for example, you would have this KPZ universality class. As far as I know, you cannot get them from.
Yes, for the different. Any other questions, comments?
This follow factor
Yes,
seems to be bizarrely robust.
yes.
But so if I go back to the set, it's independently the two densities, am I?
No. It's density 1 and density 0.
Do you need both of those?
Yes.
Right.
Yes. Otherwise, it's a function of rho A and rho B. But you see, this one word has attracted a lot of interest because people found this one third, and not only this one third, the whole distribution when rho 1 is 1 and rho 2 is 0, the whole distribution is the same as one which was discovered by Levitov. And okay, I don't know. I have the name, another Russian, Lesovin. Okay. And what they consider is the following: you have fermions, non-interacting fermions, and these fermions goes through a channel. So you inject fermions here, and you let them go, and this is a disordered channel. And so they looked at so this is called Schottner, 2 squared over Q. And they find, what they find is that, okay, because they are talking about charged particles, they find that this is the charge of the particle divided, they don't count the number of particles, they count the charge by 3, which looks a little strange because you have particles which have charge Q, okay? So the electrons, maybe there is a minus, I don't know. But anyway, they find 1/3. And okay, it's like you would have particles with a charge 1/3 in the system, but this is a calculation and which has been known for a long time. But what these people have done is that they have calculated all the cumulants, and all the cumulants are exactly the same as for the set when density is 1 and rho 2 is 0. Exactly the same. And I don't know, some people wrote some kind of theory, which large-scale theory for this system, and somehow it resembles the theory that I mentioned here. So this is one short story.
Are you saying that there is a now clear understanding of the equivalence?
Okay, there are papers who at some stage reach the same equations. I cannot say that I am very, for me, they are easy to study in paper. But essentially, you get this thing, not only these two cumulants, but just if you say that the transmissions here, it's just a random matrix. And if it's a random matrix, you get all this thing.
Okay. Any other questions, comments? Okay. If not, let's thank Bernard again for this very nice lecture. So now we stay in Cambridge till the end of next week.
Yes, so
yeah,
anybody
if you
who
have
has time or to talk or so, I would be very happy.
Okay, thank you.